So here we begin Chapter 2. Chapter 2 deals primarily with atoms as well as the periodic table.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, plutonium, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium, manganese and mercury and molybdenum and magnesium and dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
So we have our introduction to the periodic table. Old song written by Tom Lehrer, where he put all the elements into one song. So we're going to start with some history here. And this idea of trying to figure out what matter was made of has been around for a long period of time. And it goes all the way back to ancient Greece, where they came up with this definition, or this term atomos, which literally stood for unbreakable. And it was the smallest particle, one that cannot be cut further. And sort of over the next 1,000 to 1,500 years, there wasn't a lot of development as it went in terms of trying to figure out what stuff was made of. But by the early 1800s, there were a couple of ideas. And there were the laws of mass conservation, which said that mass cannot be created or destroyed in a chemical reaction. There was the law of multiple proportions, which said that elements combine in whole number ratios to form compounds. And finally, the law of definite proportions, which says that a compound always contains the same number of each element regardless of its source. And what we mean by this is we mean that water, for example, is 2 hydrogens and 1 oxygen. Doesn't matter where the water comes from, it's always going to be 2 hydrogens and 1 oxygen. So in 1808, and one of the interesting things that we see in science is when we talk about history or ancient history, as far as chemistry, something like chemistry goes, 1808 would be considered sort of ancient history. Before the early 1800s, we really don't get much that we would recognize as chemistry. And so John Dalton came up with his atomic theory in 1808. And while he didn't get everything right, we're still going to use it as a starting point. And we're going to see what he got right and what he got wrong. So Dalton had 5 main ideas for his atomic theory. First is that he said matter is made up of tiny particles called atoms. And so we can see, over 200 years later, that this was pretty good. I think we can say he got this one right. Now, he also said that all atoms of an element are identical. Now, this one's not completely right, because the idea of an isotope was not yet known. In fact, it would be quite a while later before we would discover what an isotope was. And we'll talk more later on about what isotopes are. He said different elements were made up of different types of atoms. So he got that right. He included the law of definite proportions as part of his atomic theory, and that one is definitely correct. And then finally, he said that in reactions, atoms are not created, destroyed, or converted to other atoms. And we can understand that he got this one wrong. The idea of nuclear chemistry, things such as fission and fusion, the type of chemistry that led to nuclear bombs used in World War II, or that leads to nuclear reactors that we use for power. None of that chemistry had been discovered yet. So the idea that we can fuse 2 atoms to form a larger atom, or we can break an atom apart to form a smaller atom, those ideas would not have been known to him at that time. So over the next period of time, a lot of work went into trying to figure out what are these things, these atoms made up of. And so one of the most famous experiments, and one of the most important, we'll look at here. So this experiment dates to 1897 and J.J. Thomson. And this experiment is commonly known as the cathode ray experiment. And we can see a rough diagram of what was here. Now, you notice these lines here slightly cut off in this diagram, and that's because this was connected, and there would have been some sort of voltage supply up here. And so this voltage supply was set, and it was run through this circuit. And you can see over here was a positively charged plate and a negatively charged plate. And what Thomson found, and he repeated this experiment over and over and over again using different metals, but regardless of what metal he used, the same result occurred. And so he could see that clearly this beam was diverting up towards this positively charged plate. And so that told him that whatever this flow was that was going through here, it had a negative charge. and he ended up calling this particle an electron. So that was the first of our 3 subatomic particles that they were able to prove the existence of. Later on, a modification of this experiment led to the discovery of the opposite charged particle, the proton. But it wouldn't be for another 30 years, or actually a little bit longer, that they would discover the third particle. The third particle ended up being the most difficult one to discover, that being the neutron. And the reason it was more difficult to discover was that the neutron being uncharged, you couldn't use an experiment like this. But even before they proved the existence of the neutron, they knew that there had to be a third particle, because it was clear that the combination of all the protons and all the electrons didn't add up to sufficient mass to account for the mass of different atoms. But at this time, Thomson came up with a model for the atom. And unfortunately, as we're going to see, he got most of it wrong. But he called this, or this has become known as the plum pudding model. Again, this is what Thomson came up with. And what he defined this as is that the atom was basically a giant sphere, and most of that sphere was positively charged. And then the name plum pudding gets derived from the fact that then he proposed that the electrons were just these little things sort of stuck in our sphere of positive charge. So not too long after that, we go to 1911, and Ernest Rutherford did another very famous experiment, which we'll see a diagram of here. This is known as Rutherford's gold foil experiment. And so if you think about Thomson's model that we just looked at, Thomson's model basically says that most of the atom is this sphere of positive charge. And so if we fire things at an atom that have positive charges, then they should be affected by it. So what Rutherford did was he started with, you can see this radioactive source at the bottom left. And this radioactive source fires out alpha particles. Now, an alpha particle is a helium atom that's missing its electrons. Now, what were the results? And what did he do? So what they did was they fired these alpha particles at a piece of gold foil, and then surrounded the entire thing with a detector. What they found was that most of the particles went straight through the foil. They weren't deflected, nothing, they were not affected in any way. And so what that told Rutherford is that most of an atom is made up of empty space. And so that alone was able to disprove Thomson's plum pudding model. In addition to that, they found some particles were deflected by small angles. So that told them that some of the particles, did somehow get affected by mass contained with the atom, but that most of the mass of the atom is empty, or most of an atom is empty space, and just a very, very small volume is where the particles are. and then every once in a while a particle would just sort of hit the atom and bounce back. So with this, they had to throw out Thomson's model of the atom. And so around that time, then the next theory that came into being was the Bohr model. And many of you may have seen the Bohr model before. In fact, I would guess that most of you have probably seen the Bohr model in some sort of previous science course. Now, hopefully you were also taught that the Bohr model ends up not working. It's actually well out of date. But leads to, unfortunately, some people still see this as the current model of the atom. And it often leads to some rather unfortunate situations. So a little over 10 years ago, I guess 2008, so January of 2008, my wife and I were at the Detroit Science Center. And we decided to sit in on one of those films that they show at science centers, and this one was called the 10 Most Important Things in the Universe. And they go through it, and overall it was pretty well done, but they get to the most important thing in the universe, which they decided to define as the atom. Well, they finally show it, and they put a diagram up, and every single thing they put up shows the Bohr model of the atom. So at that point, I wanted to go and complain, but I figured my wife and I had only known each other for about 2.5 months at that point, and that might not go over real well. On the other hand, I guess I shouldn't have been too worried because, she broke up with me a few weeks later. But don't worry, the story has a happy ending. We've been married 10 years now. But the Bohr model does get a few things correct. And what it does get correct is, if we look at the model carefully, we see the model is made up of a nucleus at the center. That's where most of our mass is. And that the electrons are somewhere outside the nucleus. Now, the electrons don't orbit in these nice, neat circles like Bohr proposed that they do, but the electrons are outside of the nucleus, and we will get into much more detail about where the electrons are later on in this course. So we can sort of summarize. We have three main particles, three subatomic particles. We have the proton. Protons have a mass of just over 10 to the minus 24th grams. They have a +1 charge, and we find them in the nucleus. We also have neutrons. Neutrons have almost an identical mass to protons. In fact, you can see that even if we only record their mass to 3 significant figures, they would actually be exactly the same. Neutrons are overall neutral charge and also found in the nucleus. Our third particle are the electrons. And they weigh significantly less. approximately 10 to the minus 28 grams. Electrons are negatively charged and are, just easiest to say at this point, not in the nucleus. So let's bring up the periodic table right now. This is our current periodic table. As I said earlier, we now have 118 elements, and you can see them arranged here. For every element, you see we have 4 pieces of information contained on the periodic table. What is that information? So if we look at any element, and we'll look at francium here, for example, we have the number 87 up at the top left. That's known as the atomic number. We'll talk more about what that means later. We have a symbol for the element. Every element has a 2-letter symbol that we use as an abbreviation. We have the name, and we have the mass. Now we want to be careful. Most of the elements have very, very logical abbreviations, but there are some that do not. And we will point out the examples here. We have sodium with an abbreviation of Na for natrium, potassium coming from kalium, iron over here from ferrum. We might not think of copper as being not a logical one because it begins with the same first letter, but you notice there's no U in the word copper, and this comes from cuprum. Argentum for silver, aurum for gold, hydrargum for mercury, wolfram for tungsten, plumbum for lead, stannum for tin, and stibium over here for antimony. All right. Now, what do the atomic number and the atomic mass tell us? So let's go to an older periodic table. So if we look down at the bottom of our current periodic table, element 101 is named Mendelevium, named after Dmitri Mendeleev. And Mendeleev is credited as having discovered or put together the first periodic table. Now, Mendeleev is not the first one who tried to organize the known elements back in the 1800s, but he ends up receiving a lot of the credit. Now, here's what his periodic table looked like. Now, why does Mendeleev get so much credit, whereas others don't? Well, one of the main reasons is that you see Mendeleev left some blanks on the periodic table. And the reason he did this was he was making predictions. There were no elements that existed in these spots, but he was making predictions that there should be an element there. And in almost every case that Mendeleev made one of these predictions, he ended up being correct. The problem that Mendeleev had, and had a lot of difficulty getting past, was it was common to think that we should organize the elements in order of increasing mass. If we go again to our modern periodic table, you'll see that as we go from one element to the next, that for the most part that does happen. But there are some places where we go from a higher mass to a lower mass. For example, over here, iodine, which is to the right of tellurium, has a lower mass. Same thing is true for cobalt and nickel, 58.9 to 58.7. And we can find a third example down here, thorium and protactinium. So this problem wouldn't be solved for quite a number of years. And it would finally get solved around 1910. And the individual who discovered that was someone named Henry Mosley. And you can see some information here that we have about Henry Mosley. So Henry Mosley figured out that we should use what's called the atomic number to organize the elements. Now I'm guessing most of you have never heard of Henry Mosley. And the reasons for that are probably this. Unfortunately, he died at just 27 years old. Because Mosley, with the outbreak of World War I, decided that he should leave his research behind and go volunteer to be in the British Army. And unfortunately, in 1915, he was shot and killed during a battle in Turkey. And so, to a large extent, the name Mosley has been lost to history. Mosley very likely would have won a Nobel Prize, but unfortunately, they no longer award Nobel Prizes once someone has died. So, what is the atomic number? Well, the atomic number is equal to the number of protons in a molecule. The atomic mass is, in general, equal to the number of protons plus the number of neutrons. And then as long as an atom is neutral, then the number of electrons will be equal to the number of protons. Now, obviously, an atom is very, very light. So when we look at those numbers on the periodic table, what is the unit that we use for those? So the units are what we call AMU, or atomic mass units. How much is an atomic mass unit? Well, in theory, the definition of an atomic mass unit is that it's equal to 1/12 the mass of a carbon-12 atom. But we can also calculate that. And it's approximately equal to 1.66 times 10 to the minus 24th grams. So again, it sort of re-illustrates our point that atoms are extremely small and we need a lot of them to add up to anything of any significance. So this is where we ended for March 11th or March 12th. In addition to this series of video files being posted on Blackboard, I will also post the PowerPoint files that I used to make these. Whether those are helpful or not, I'm not sure at this point, but I will post those so that you have them. Any questions that you have on material, please feel free to email me. I'm also looking into figuring out some sort of method for setting up some sort of virtual office hours. and hopefully I will figure something out for that. I'd like to be able to do more than just email in that regard, but I will let you know more about that either later today or at the beginning of next week.